We saw in the last clip the simplest of all MO diagrams, that for H2. And in this clip, we'll go on to a more complicated MO diagram, that for F2. It will be an example of a one-figure MO diagram. And as we're moving to F2, we're going to have to start looking at the 2s and 2p orbitals in addition to the 1s orbital. So F2. The MO diagrams we're going to be drawing are only valence atomic orbitals, only the 2s and 2p. So when we consider F2, we'll only have to look at 2s and 2p. But we are going to have to look at 2p. They have a different shape, and let's see what some of those shapes are. We have the 2p on, they could come together like this. The 2p orbital on one fluorine could directly point to the 2p orbital on the other. That's called a sigma bond. And that's a constructive interference by the Hofmann ansatz that will lead to wavelength lengthening, and that will be an energy lowering procedure. But there's another way. Can you think of what it might be? What's the other way that it might be that you could get the p orbitals to come together, that they have some constructive interference? The other way you can do it is you get them to go side by side, both pointing the same way. So on the top half, they're in phase, and on the bottom half, they're in phase, and that's called pi. So sigma bonds are sort of like this, and then pi bonds are like that. Okay, so we're going to have 2s and 2p, and we'll have sigma and pi bonds in F2, though the pi bonds, because they are responsible for multiple bonds, are quite weak for fluorine, because fluorine makes very poor multiple bonds. The procedure of the one-figure MO diagram, since it's a quite general procedure, is a little scary. There's just a few key ideas that we need to learn at the end of this lecture. So it's a lot of words. I'll just tell you what the key ideas are. Okay, first, we're going to be looking at the valence fluorine atomic orbitals, which are 2s and 2p. Due to penetration, 2s is much lower in energy than 2p. Calculations and experiments show that the 2s orbital, atomic orbital fluorine, is at minus 40 EVs. That's a unit of energy. And 2p is half of that, minus 18 EVs. And roughly 100 kilojoules per mole corresponds to 1 EV per molecule. So they're around 2,000 kilojoules per mole separate in energy, which is a large difference. Okay, and how do these rules play out? First, it's a diatomic molecule. The left atom of the diatomic molecule will be on the left, the right atom will be on the right. And the molecular orbital diagram is OS an energy scale. And finally, on this energy scale, we need to draw the 2s and 2p orbitals. There's one 2s orbital per atom and three 2p orbitals. And now, let's look at those 2p orbitals. Look at the 2p orbital on the way left. To which of the orbitals on the right? So we're looking on the left fluorine, on the left side of it, at that p orbital that's pointing straight up. To which one of the orbitals on the right fluorine does it make a pi bond? So on the right side, there's the left, middle, and right. Which one makes a pi bond with the left? Put it in chat. That's terrible nomenclature. I'm going to change the nomenclature for the next questions. So, the one that's like this makes a pi bond with the one that's like this. The one that's like this, pointing straight out, makes a pi bond with the one that's like this. What about the two together? They're coming together like that. What are they making? A sigma bond. So the fluorine 2p orbitals can make two pi bonds and a sigma bond. And whenever you add the two, by the orthogonality mixing principle, we're going to have to subtract the two. Is that clear in our minds? And finally, we have very low energy, the 2s orbitals, and they will come together in the way that we just saw for H2. So those are some of the possibilities. We see the possibility of the pi bond. We see the possibility of the sigma bond. We see the 1s orbital, the 2s orbital bond. which is, by the way, also a sigma bond. And but aren't there other ways of mixing them? And that's where this is the rule that we want to learn. Rule number 4: when mixing left and right orbitals, mix the ones that are geometry equivalent, that look the same. So the 2s looks like the other 2s. It's right to mix the 2s with the 2s. The sigma pointing 2p is geometry equivalent to the other sigma. So it's right to mix the sigma. And it's right to mix the two pi's because they are geometry equivalent. So rule 4 is super important. And the pi bond has much less constructive interference. And fluorine is terrible at making multibonds anyway. So the sigma bond will be stronger than the pi bond in energy. So let's see what that mixing looks like. And it's a lot of info in the next slide, and we'll just go it from the bottom up. Okay, first we see that the 2s on the left mixed with the 2s on the right, just the way we had before, and I put in parentheses the melded picture. Then when we look at the fluorine 2p's, yes, the sigma bond interaction is the strongest. But the sigma antibond, the destructive interference of the sigma, which is sometimes called sigma star, is the highest in energy because it's the most destructive. The pi bond is between the two, and the pi destructive above the two. And so, just using these simple principles, we have actually developed the MO diagram of F2. All we have to do afterwards is fill with electrons. Every orbital gets a pair of electrons. Each fluorine has 7 electrons, so 7 times 2, 14 electrons. We fill 7 orbitals, as I've done in the middle. There are a few more rules that I just want to quickly go over. You might have additional orbitals left over. Then you're going to you should always do them in the order of strongest bonds to weakest bonds. We really didn't need that. And then rule we will need is this rule number 6. Orbitals that are initially close in energy interact better than orbitals that are far apart. So the MO diagram is a complicated procedure. You'll learn more about it over the next few lectures. But again, it's just mix orbitals that are geometry equivalent to each other whenever possible. And it's an energy diagram, and 2s is far below 2p.